Hello class, this is Dr. Anderson and we are finishing our exploration into pulmonary physiology, and we need to talk about control of respiration. So briefly, here are some learning objectives. We are going to talk about the central structures that generate respiration, and then what kind of information from the periphery that can feed back and influence respiration. And we're going to talk mostly about chemoreceptors. There are some central chemoreceptors in the brain, and there are some peripheral chemoreceptors near the baroreceptors. And we were going to talk about how pH and PCO2 and PO2 all regulate ventilation. So here's a diagram from Kopsted's pathophysiology, and in this diagram you see in the medulla we're going to have some chemoreceptors, and then we have some cells that stimulate inspiration and cells that stimulate expiration. So the inspiratory cells send information to the intercostals and the diaphragm, and that tells us to breathe. We can simply stop stimulating the inspiratory cells and exhale, but we can also exhale actively if we activate these expiratory cells. So those are in the medulla. We also have some pontine nuclei, and that would be the apneustic center and the pneumotaxic center that influence respiration. The apneustic center was named because when you stimulated this or tried to isolate its activity, an animal would take a big breath and then just hold it forever and ever and ever and ever and ever and ever, and they wouldn't breathe for a long time. So it was called the apneustic center. But actually it excites the respiratory centers in the medulla. And then there's the pneumotaxic, and those inhibit the respiratory centers. So if you have more apneustic stimulation, you will breathe more deeply. If you have more pneumotaxic stimulation, you will breathe more rapidly, and those are sort of working together to influence these respiratory cells in the medulla. Notice there are all kinds of things from the periphery that can activate the central centers. So proprioceptors, just the active moving can feed back and increase respiration. That's something that happens with exercise. We are going to talk about the chemoreceptors in a great amount of detail. And then there are kinds of stretch receptors. Some people talk about pulmonary baroreceptors, and then certainly cardiovascular baroreceptors can have influences on breathing as well. And we could have other things in here like pain and voluntary activity and that sort of thing. So here shows the nuclei in the medulla. So there's a dorsal respiratory group and there's a ventral respiratory group, and we have some cranial nerves that are supplying sensory information, and then we have some cervical spinal nerves that are providing motor information. If you remember from anatomy, 3, 4, 5, those are the levels of the cervical spinal cord. 3, 4, 5 keep you alive. That's where the motor neurons come out of the spinal cord. And here's an interesting diagram showing you an electromyogram of what's going on in the diaphragm versus intrapleural pressure. So remember, intrapleural pressure is negative, and it gets more negative, and then it goes back to its relatively negative value. Then it gets more negative, then it goes back to its relatively negative pre-inspiratory level. But notice, while we're inspiring, there's a higher and higher activity, or a higher frequency of activation in the diaphragm. And then it stops. And then we exhale. Then the activity builds up again. We inspire, and then it stops, and then we exhale. So similar studies have been done in animals looking at the respiratory centers, and there are cells that seem to have pacemaker activity, and they activate in a ramp pattern, and they will increase in frequency and then they'll stop. While action potential frequency is increasing, the animal's inhaling. When it stops, the animal exhales. So this is quiet respiration, and this should fit in nicely with what we've talked about already, that you have to activate muscles in order to inhale, but to exhale passively, all you have to do is relax. Here's another diagram talking about all the inputs to the respiratory centers, and in this case, it's putting the medulla and the pons together. So there are all kinds of stretch receptors in the lungs and irritant receptors. If your lungs are highly stretched out, that will inhibit respiration so that you will exhale. If you're down at very low lung volumes, there are other stretch receptors that will encourage you to inhale. J receptors are found outside of the alveoli, and when your lungs are congested with blood and there's some alveolar edema, J receptors are activated, and that will tend to make you breathe in a very shallow, rapid way. Of course, we can control respiration voluntarily. I can breathe fast if I want to. I can hold my breath if I want to. We are going to talk about how the central chemoreceptors tell your brain about the blood chemistry. And so those are central and peripheral types of receptors. Then, of course, spinal motor neurons. The phrenic nerve goes to the diaphragm, to the intercostals, accessory muscles, the diaphragm, so you can respire. And then we have muscle proprioceptors, and this is important at the onset of exercise. The minute you start exercising, your ventilation goes up, because the proprioceptors tell your brain, oh, we're working really hard, our metabolism is going up, so why don't you start the ventilation now. This is a great example of what's called a feed-forward mechanism. The principles that you're regulating by negative feedback have not changed yet, but here you have some information that anticipates changes in blood chemistry and gets the ventilation going ahead of schedule. So what in the heck is going on with these peripheral chemoreceptors? Remember, in the carotid body we have some baroreceptors. We also have chemoreceptors in the carotid body and in the aortic arch. They sense arterial blood, and they're going to sense PCO2. They're going to sense pH. And particularly the carotid bodies are going to sense O2 through cells we call glomus cells. And the partial pressure of oxygen has to get below 60 millimeters of mercury before we set off the glomus cells. So if your oxygen is too high, it's not really affecting the chemoreceptors. It's when your O2 gets really low. And I'll show you more detail about that in just a bit. So here's a diagram from your textbook Vander. Notice our x-axis is arterial PCO2 measured in millimeters of mercury. And then our y-axis, or our outcome variable, is minute ventilation in liters per minute. So around 40 is a typical arterial PCO2. Notice if CO2 increases to 44 millimeters of mercury, then ventilation goes up to about 10 liters per minute. So you have an increase from 5 to 10 liters per minute with this increase in pulmonary arterial PCO2. And if your CO2 goes down, then your ventilation goes down as well. So there's a very strong relationship between arterial PCO2 and minute ventilation. Now here's the oxygen relationship I was alluding to a bit ago. Normal resting arterial PO2 is about 100, 95 to 100. Notice PO2 can go to 100, 95, 90, 80, and we're not getting much of a change. 70. Now notice around 60 is when things start to change. So very little change before above 60. At 60, a large increase in ventilation. So this is what's called the hypoxic drive. Hypoxic drive. You know, if you'll just come back here, a very small change in PCO2 caused a rather large increase in ventilation. But we have to have a very large drop in PO2 down to 60 to start to see an increase. So our hypoxic drive is not normally in operation. A hypoxic drive would come into play, say, when we went to altitude, and because the air is thinner, atmospheric PO2 is going to go down. Then arterial PO2 could be decreased in the body, and that would stimulate ventilation. pH also has a strong influence on respiration. So notice that typical physiologic pH is 7.4. That is 40 nanomolars per liter. We actually don't carry around a lot of hydrogen ion. So 40 nanomoles per liter. We go up to 42 nanomolars, 44 nanomolars, and now you see a similar relationship between pH and ventilation and CO2 and ventilation. As hydrogen ion concentration goes up, we drive ventilation. As hydrogen ion concentration goes down, we are going to inhibit ventilation. I should have put a little question slide in here. So I'm going to leave it at that. Remember our learning objectives. I need to find my backspace. So what kind of receptors are we getting information from? So we have chemoreceptors, we have proprioceptors, we have stretch receptors, we have irritant receptors. Where are the central chemoreceptors? They're in the brain, near the in the medulla, near the respiratory centers. The peripheral chemoreceptors are near the baroreceptors. When our arterial pH gets low, we drive ventilation. When PCO2 goes up, we drive ventilation, and PO2 has to go down below 60 millimeters of mercury to again drive ventilation. Which is most important? PCO2 is the most powerful regulator of ventilation. So I'm going to end it here, and our next presentation will be on pulmonary pathophysiology.